and just making magic underneath. It is starting our stream. I hope so. Facebook is running. I hope so. So hello everyone. Today on the third day of our conference, we are starting from Oren, Eini. So I hope you will have a nice conference today too, like we had yesterday, and the first day was okay. Let's forget about it. So without further ado, Oren, I'm super happy you are here today. Oren is, I hope you all know Oren. We also known as I and Ryan, if I'm spelling it correctly, probably not necessarily. You are creator of the RavenDB, so pretty popular library, pretty popular, I'd say, product that is for sure performance related. So we hope to have a lot of knowledge from you about that. And by the way, I looked at your blog. You have posted over 7,000 posts. So it is
In almost 16, 17 years, yeah.
yeah, that's an awesome amount of knowledge there. So if you are interested, look at Oren everywhere. We will find it for sure. So Oren, I'm super happy. We are all super happy. Have a nice talk. Then I am going to the backstage, and the scene is yours.
Thank you. So welcome everyone. Today I want to talk about something that is a lot of fun. Performance and how to get it to be faster and faster. And there is this old adage about um, performance doesn't matter, or it usually doesn't matter, and stuff like that. And it's sort of true. For the most part, start with getting the software correctly and then move for performance. So I want to tell you my story about how we built RavenDB and how we used RavenDB to how we made RavenDB faster. So here are some details. So RavenDB, we started out in 2008. Just to give you some context, .NET was at 3.5. That's a lot of time ago. Like seriously, 13 years ago. And at the time, it was a fairly typical .NET application. It had a client API and it was Windows only. RavenDB itself is a NoSQL document database. It's basically stored JSON document. It is distributed, have the ability to query, operate, aggregate, and much of stuff like that. I'm not here to talk about RavenDB. It's almost incidental to this talk. It's just the background. So I want to talk about a really interesting thing that we noticed. And I want to give you a timeline of our releases. So I started designing RavenDB in 2008, started writing actual code in 2009. 2010, we had a release, 2013, 14, 15. Perfect. At this point, we are deployed in hundreds, thousands of locations. We have lots of customers, and every single time we made a release, and I checked, we had this note, improved performance. And that was a true note. In every single case, we're able to improve the performance, sometimes significantly. And yet, and at some point, we hit a wall. We could not get it to be anything. We couldn't get it to go faster. We just, and the problem was that we hit a wall not in terms of an algorithm or an approach. The entire code base fought against us in doing that. And one of the most common scenarios that we had to deal with was looking at GC, time under GC of over 85%. Just to give you some context, that means that we're spending almost no time actually doing useful work. Most of the time we just spent, collecting garbage that we did and being basically being bottlenecked. So that sucks. That sucks quite a lot. And I really wanted to fix that. But the problem here is that, again, we have at this point, remember, this is 2015. At this point, we have 6 or 7 years old code base. It had its own character at this point. And you couldn't make those modifications. Remember, this is a standard at the time. It was a fairly standard .NET web application. At that point, we rewrote it to have, instead of the ASP.NET server, we wrote our own server. We made a lot of modification. We had a lot of caching, optimization, blah, 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 blah. Didn't work. I mean, it worked. We got better performance, 10, 15% in some cases. That's amazing. But I didn't want 10 or 15. I wanted 100, 200, 500 better. And we could not do it with what we had. And we look into what it would actually take to make it happen. And it turned out that this is basically everything. One of the most common issues that we had was memory utilization and GC pressure. And in order to do that, we had to, well, touch everywhere we allocate in our code. That's pretty much everywhere. So we cannot do that. The other issue was that this is a very dangerous thing to do. In terms of business, we have to take a year or two to stop and do that. We have to, there is the second system syndrome. If you're familiar with Joel Spolsky, he's an awesome writer. He has a blog post talking about the mistake that Netscape made when they decided to write from scratch. And read it 10 years later, and hey, Firefox is all over everywhere. Read it now, Firefox is at 5-10% of the market. Interesting numbers. So let's see what we had to do. Given the risk involved, in order to be worth it, it had to be far faster. If it's not 10 times faster, there's no point talking. We have to have the same features. And one of the key things that drove to this was the knowledge that we have now 5-6 years in production, knowing where it hurt us. One of the things that we did, which I now regret, was give up on backward compatibility. That was a huge issue for users. That's a mistake, but that also allows us to make significant changes to the way the system works. So let's talk about what we actually did. How can I be fast? And in general, that is really hard to answer. I can do less, but what does it mean do less? How do we do less? I can figure out smarter algorithm. Or I can try to do something far more interesting and try to reduce what I promise. For example, RavenDB is a transactional database, which means that if we commit a transaction, we guarantee that the data is going to reside on disk, no matter what. Other databases, for example, Redis, skip that part. They said, oh, I'm explicitly not transactional, so Redis can be really fast because it does all operations on memory. We did not, there are some things that I'm willing to give up. Transactions, no. Transactions are there to stay. So we had to figure out how to manage that and what we could change in our approach to deal with things. So one of the obvious things is let's not be stupid. Figure out the right algorithm to the task, blah, blah, blah. You're probably familiar with this. I would point out that at some points I managed to have an algorithm that was not n squared, but n to the power of 3, because that's just for amateurs to just be n squared. Now, here's the deal. We have done nothing but those kind of optimizations for several years at this point. It's not sufficient. And the problem is not that, oh, you're using bubble sort. You can use a team sort or something like that. The problem was, oh, you are doing something that is inefficient on every single layer of the stack. What do you mean by that? Let's consider what it costs us to read a document. So a user goes to a RavenDB database and says, give me document X. And RavenDB now has to figure out where that thing is on the disk. It needs to read it from the disk. It needs to send it to the user. Maybe it needs to do some operations on that. Every single piece of that was written to work and to work correctly. But we didn't consider performance to the appropriate level. For example, we would allocate in some cases many times. Here is a really, really annoying bug that we had to deal with. Consider what happens when the disk is slow. That sucks, right? You don't want to do that. So here's what's going to happen when the disk is slow. You're going to be slow overall. So the natural thing to do here is, oh, well, we just use a cache. Okay, so if we store a JSON documents as just binary data on disk, now when we read it, we need to parse that into an actual JSON document, not just some bytes. And then we stick that into a cache. So next time that someone is looking for that document, we can skip the parsing and we can skip the reading from disk. Everyone wins, right? What happens when the size of the number of documents that you get is too big, but you start having memory pressure? Well, I wasn't stupid. I wrote the code properly. What does it mean properly? If the cache detected that there is too much memory, do you know what happens? It starts clearing things from memory. So it would balance itself out. Now, remember, we wrote everything in managed code. Pretty standard .NET application. Now, here is what happens. I read a document from the disk, read it to memory, make it into a .NET object, put it in my cache. The cache is going to keep it alive. I'm under memory pressure, so the GC is going to run. Every time that it runs, it's going to push the document in the cache to the next generation, which means that under memory pressure, very quickly, we are going to end up with a lot of data in the Gen 2 collection, which doesn't get evicted all that often. At the same time, my cache detects that we are under memory pressure and start clearing things from the cache. But I'm clearing that from the cache. I'm not clearing that from memory. I have to wait for the GC to do that. But the GC is saying, oh, that thing is in memory for a while. It's in Gen 2. I'm not going to collect that. At the same time, I'm not benefiting from my cache because I cleared that because of the memory pressure. So now I have to hit from high how IO and slowness from that, high CPU because the GC is always running, and the system is basically slowing down. From the feature that is explicitly meant to make it go faster. We added, in some cases, a flag, don't use the cache. Performance improved by order of magnitude. And then I went home crying. That's not how it's supposed to be. Now, this is one example of several that we had to deal with. And how do I fix that? I actually need the cache in most cases, unless I am under memory pressure, in which I don't need the cache, but then I actually do need it and not much further stuff like that. This is what I mean by having a problem at the architecture level. Let's talk about something pretty simple, and I want to give you something that is concrete. When we need to route a request, a user is sending us this GET request, and I need to call this method. So you can see here the diagram. Somewhere here, this is the part that we care. This is what I call routing. So I wrote a very simple benchmark. This was in 2016. We were about 6 months into rewriting the architecture of RavenDB. And you can see here that with 100 clients, 500 requests each, so a total of 500,000 requests, we're getting really respectable numbers. I mean, seriously, that's quite nice. Now, this thing was, I don't remember what the algorithm was. This one used a tray, so it was faster. And you can see how much time we're spending when running this. Interesting. We wanted to be faster than that. So I started to look into exactly what's going on. And this is from the NaNCFX code. I want to show you some things. This is a path is a string, and this is do an allocation. This is do an allocation. Let's look at the code. Here, this is the profiler output. And what you can see here is that I have Eini, and I create a dictionary in here. Notice that I'm doing that 2.5 million times. I'm calling Eini 3 times per route to create a dictionary per route called select. Here is another dictionary that I'm creating 2.5 million times. So in other words, just in this location, I'm wasting a lot of my time, like significantly a lot of my time. And I can see that, okay, 1, 2, 3, 4 allocations. You can see that even in here, I can see that they have garbage collection kicking in. That's horrible for performance. So I can try to do better. So the first thing that I did was figure out what's going on. Some routing systems use regexes and were insanely complex. I decided that I don't need everything. All I needed to do was to say, hey, you know what? I'm going to look at the routes that I have. Most of them are ASCII only. There are some parameterized values, but for the most part, we're talking ASCII only. That simplifies things. I have mostly fixed paths. I'm not allowing any allocation during the standard operations. And the code itself is, I'm willing to accept that it's going to be ugly. Now, let me show you something. Where is it? There we go. So here we go. So this is the relevant code. You're not expected to understand or follow that. Absolutely not. But you can see that all of this code is doing fairly nasty things. But the whole point of this, by the way, just so you understand, this is something that intentionally allocate too much data. So in here, if I'm doing the search, I'm always doing this. And this is guaranteed to always be able to work and handle the captures and everything without, because my assumption is that I have about 400 or 500 routes. It's cheaper for me to just run everything in memory, expand everything, and not really think about it. Now, let's look at something that is even more interesting. I can adjust. Let's look here. Let's say that I have a resource locator that needs to do a key in this case is some value that I have to run in a case insensitive manner. Well, in almost all cases, in almost all cases, the casing that I'm going to use is going to be fixed. It may not necessarily be the orthogonal value, but it's going to be fixed. So let's look at what I'm doing here. I'm saying let's look at the items version, and if it's in here, great, I can return it immediately. If not, let's look at his here. And why does this matter? This matters because if this does not exist here, but does exist here, I'm rebuilding this items collection, which is now I'm teaching that about the new version of the casing that I have. Next time I'm going to get here, this is going to be okay. Now, notice a few things. This is actually concurrently safe value. Every time that I have a miss in here that is a match here, I'm rebuilding this dictionary. I'm doing that in an intentionally wasting memory. And notice that if this is happening concurrently, two requests may do that at the same time, because that means that all of this code in general is optimistic. Worst case, I do the work again, but again, I'm assuming mostly fixed values. So very quickly, I will learn all of the unique cases that the user uses, and then this is effectively static code. And it's static code that doesn't need atomic, doesn't need logs, everything just works. Now, here is to give you some idea about the difference in numbers. This is calling try-get value when I'm using case insensitive hash code. So this is a dictionary that uses string compare, invariant, ignore case, something. Look at the costs. Conversely, this is the cost without it. It's effectively free. Look at the numbers. Now, here is where I looked at things. So this is the default Microsoft routing. And again, this probably might have been better. I'm talking about experiments that we did in 2016. So for 2.5 million calls, this is costing us quite a lot of time. But okay, this is on a profiler, doesn't read it that much. Except that if I'm comparing that to the non-CFX version, this is 23 times faster. If I'm comparing that to my version, look at this number. 2.5 calls at under 2 seconds. 2.5 million calls. And this is under the profiler. And this is an example of setting out a fairly simple goal, limiting ourselves as much as possible. People think that, oh, we have to be extensible and be able to accept and everything. No, if you want to have performance, you have to accept limits. Limits are your friends. You can ignore these scenarios, they aren't relevant. The fact that I'm using the ASCII instead of Unicode here meant that I had a lot of additional optimizations. Now, let's look at another example. And again, I'm talking about here micro optimizations almost. This is the version of dates that we use. This is how it looks like. This is what we call. So at a time, 750 dates per second. This also does quite a lot of allocations. We wrote this method. Now I'm going to show it to you. And again, the point isn't to scare you. The point is just to show you what we're doing here.
Oren,
this is a lot of quite gnarly code.
Sorry to interrupt you, but could you zoom out it a little? So because this particular, oh, exactly.
Yes.
Thank you.
Thank you. So this is gnarly code. You can see here that we're doing, where is that? So we are passing a pointer to a char buffer, which we accept from creating this string version and passing it here. By the way, this is relatively old code. So I think the last time we changed was around here. This is where we actually wrote this. And so 2015. At this point, I think we can do it more easily if we wrote it like this. That would be nicer. But the whole idea is that we're getting there, and now we are modifying this directly, and I have 4 digits and a whole bunch of other things that I'm generating in order to optimize that. And again, we have a single allocation that we have to do, and we're about 6 times faster. And here's the issue. I cannot go on doing that. I told you about the caching and the GC issues. We hit a wall. We need something better. So how do we change the actual architecture? So let's look at one of the first major things that we realized. I have this query and I want to execute that. So I have an index, I need to find it, then I have to load it from the disk. I'm loading that into a byte array. I parse the document into a J object. I extract those values to another J object, serialize it to a string, allocation, 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 allocation. Here is another really interesting fun fact. Do you see this? This is a JSON document that is 37 kilobyte in as text. This is the size when you parse that. Why is that? This is a relatively complex document. So you can see that the structure in memory takes more than the data as text. And all of this, we have to remember, also goes into the GC has a ON cost, where N is the number of reachable objects that you have. Remember the cache that I told you about? That would be one of those ON costs. So here is another issue. What's the cost of writing JSON? That was a shock to me. Notice this function. 1, 2, 3, 4, almost 40% of the cost of writing JSON is escaping strings. Absolutely insane. I'm spending that much time on this. And remember that in most cases, I'm writing once, but reading, I'm sending, I'm writing the database, the document to the database once, but then I'm sending it from the database to our users many, many times. 40% of my time is going to spend on that. I couldn't do that. So I had to do something else. In essence, what we did was give up on JSON as a storage format. What we wanted to do, we called that Blittable. There was an old graphic method called BitBlit that moved the data as is from one location to another. And the whole idea is that we're going to build a structure as unmanaged memory, just bits and bytes, that gives me the same abilities as JSON, but, and this is key, without needing to do any parsing. In essence, what this means is that I'm going to lay out all of the properties of the documents as a sorted structure, and then I'm going to point to the location of the actual value. So if I need, so I already have the structure in memory as is. I don't need to build that. I have a byte array or byte buffer, and I can work on that directly. All of the access was using pointer arithmetic, and that actually allowed me to do some really interesting things. For example, when I'm storing strings, I'm not storing just the string itself. I'm storing the raw string, but then I'm also storing another value, the number of a location of the escape sequences that I need. Which means that when I need to write stuff, I can, in most cases, I don't have any escape sequences. So I can just write it as is. To give you some idea, Uh, is it? Let's see if I can find it. So blah, blah, blah. And now what you can somewhere around here, here you go. So here is the key issue. The lazy string value, you can see that I have the number of escape strings. I can read it. And if I don't have anything here, I can just go here and copy it directly to the buffer. This is a mem copy. This is insanely fast. 40% of my time here versus effectively no cost whatsoever. We also have quite a lot of other tricks that we use. For example, we store historical data about access patterns. So if we know that, again, this is your query and you want to find a name and address, I can tell you more or less, even between different documents, where to go, where to start a binary search that would make things a lot faster. So that makes things a lot easier for us. Just to give you some idea, here are the different numbers. This is the cost of doing JSON and Blittable indexing. It's not even funny that the difference is this big. So we don't want to pay the parsing costs over and over again, because every time that we read it from the disk, we would pay that. So another really important impact of that is that if I don't need to pay the parsing cost, what do I keep in memory? Why do I need a cache? Well, just to save on reading from the disk. Remember that that will be important very shortly. We optimize the binary format for our own usage based on our own scenarios. And that had a huge impact. And the more that we have the notion of a context. A context is how we do pretty much everything inside of RavenDB. And a context is also a source to learn what you're doing. Or you're accessing this property, you have this set of well-known fields, stuff like that. And context is something that you use. You typically use it on a scope of a single request, but then the next request is going to use it as well. Which means that over time, we're able to optimize ourselves. Oh, we now know more about the environment. Let's see how that works. Now, IO is expensive, so we have to use buffers. But you know what the problem is? Buffering is super complex. There has been literally multiple PhD on how to cache efficiently. And that's something that we felt intimately. But wait, we're using the zero copy model. Instead of explicitly reading from the disk and then managing the buffers and all of that, I can just memory map the file directly and just find the data immediately. The OS is going to handle paging the data to memory, keeping that in memory. All of my buffering is now done by the operating system. And the kernel has the global view of what's going on. I don't need to worry about, I have RavenDB and a web application running on the same system, and they're fighting for resources. No, I'm going to be the nice neighbor, the one that gives you room to work and operate. And because I can operate on the Blittable directly, I don't need to have a cache. The kernel is responsible for the cache. That's huge. Think about what this means and how it works. I now am able to just hand a pointer to a memory map file and process that everything. Things such as I have this piece of hot data that I have. All those sort of things are already handled for me for free cheaply. I don't care. Everything is working. And I can, in many cases, that also has an impact on the overall system. Here's how it works. I'm going to the storage, give me the ID. I'm getting this thing. Okay, I can just pass it to the right method. And we're pretty much done. I could go on for literally hours on this particular scenario, but I want to give you some other details that we did as well. So one of the key things that we did was figure out how the GC works. So if you can avoid allocations, that's awesome. Struct, value types, all sorts of stuff like that. This is great. If you have allocation that you keep for a long while, awesome. Very short-term allocations, that's no big deal. The key here, if you have allocations that live for just enough time to kill us, and that's where we were, and that's where we had to get out of. So we had this idea of a context that lives for a long time. It has memory that it keeps for a long time, but the whole idea that context is something that use and then return. From the operating system, from the GC, from the operating system point of view, this is memory that is kept for a long term. But this is the same memory used over and over across different requests. This also meant that in many cases, we allocated memory directly from the operating system unmanaged memory, and then we run that. Just to give you some idea, there is something called Arena Allocator. And this is basically the memory that I allocated. This is the amount that I used. Every time that I need to have more memory for this particular context, okay, give me this section, give me this section, this section. Once I'm done, okay, the memory that I that uses go back here, and now I'm starting allocating from here. It might be easier to look at it in terms of code. I have some backend store, and every time that you want some memory, I give you this range. And when you want to reset, we just do this, and now we're done. This requires that you know that, okay, I'm done using everything that might be using anything that came from the arena. But that was a natural consequence of the notion of using contexts. So I want to give you live actions for this. I've set up a couple of servers in Amazon. This is a RavenDB running a single node on a Graviton instance, 8 cores, and the memory isn't really relevant. And what I have here, is another client instance. This is going to try to generate at a rate of about 50,000 requests per second. And now you can see something really interesting. At 50,000 requests per second, that include loading a particular user. So actually, that's on. What happened here is that this document does not exist. So I think that we basically return a lot of 404. So now we actually return a valid value. We're now at 40 requests per second, probably because we also have to serialize the results. But notice what's going on here. We're at 60% capacity. If I had another client to push, I could do that, and I could keep going with this. But this is a much smaller machine. Now, notice this is also our machine, not an x64, which is the typical server. I intentionally selected a server that is on the budget level to give you some idea. And again, the server is running 40, 41. The CPU is consistent. This is where we want to be. that there are no surprises even under load. Now, something that is crucial. One of the key aspects of what we did was to figure out how the entire system is operating. What do you mean by that? For example, we removed the cache in form of a memory map file, but we still get all of the benefits of reduced I/O and everything like that. But all of that code isn't there. We optimize ourselves to the way that the GC actually works, instead of and what we basically did, we look, okay, what is the sweet spot? What is the scenario that this is going to be the best for it? For example, sequential I/O is the best. How can we generate sequential I/O? The GC doesn't like us to have midterm allocation. It would like us to have allocate once and never touch it again. How do we get to that? That is a key concept that we want to achieve. And we did it by understanding what are the optimal patterns for the infrastructure that we use and explicitly structuring ourselves to take advantage of that. For example, in many databases, there is something called the page cache or the buffers or something like that. When you need a buffer from, we need a page of data from the disk, you go to that and you get that. Every time a transaction needs to access a buffer, it needs to pin it in memory, to lock it, to make sure that no one is ever going to say, oh, I need memory, I'm going to discard it while the transaction is looking at this memory. That means that every time you access a page, you have to do some atomic operation. That adds up quite quickly, especially if you have those atomic operations as something, you have a hot page that every transaction is operating. Now you have contention on that particular ref count for that particular page. In RavenDB using memory map, that just doesn't happen. And if the kernel decides that we need to do that, the kernel is actually going to rewrite the memory map for the process and handle that. Code that I didn't have to write that works to make me faster. And there are literally dozens of things like that. Oh, we noticed that the escape of strings is expensive. So we put string escaping optimizations directly into our into the way that we persist data. And that gave us quite a lot of benefits. You can see that RavenDB is still running really consistent. Same node, same thing. We can add more load to the system right now. It would still work. But from our perspective, and something that we found quite often, having better performance, and it's relatively easy to squeeze another order of magnitude, by the way, performance from the system, but that would give us higher variance. So most of our users would say, okay, I'm willing to get, you have 100, 200 milliseconds SLA under this load, and you can sustain that. That's awesome. Now it's time for questions.
Super, super nice. Thank you, Oren. Very inspiring talk. I hope more and more code will be improved after this. So we have a few nice questions. Like let's start from the middle, as it is about tooling. We have two such questions. For example, are you aware of any extension for Visual Studio or any other IDE tool that will show the complexity of algorithms you use?
No, and typically that wouldn't work. Here is the problem. The issue is typically not in a single method. The issue is not typically in a single location. It's the confluence of multiple distinct operations that you see that are super expensive. There, very recently, there was a bunch of article about scanf, and scanf is this is a C library method that allows you to tokenize things. If you call it repeatedly, it ends up being an ON square operation. And that's not something that you can figure out unless you go and read the code. And apparently this is basically how all of the C libraries are implemented. For example, let's say that in many cases, the issue might be check deduplication a list. So you don't really think about, oh, I'm doing an ON operation in a loop, which is on n square. You call a method, does this exist? And 2 layers down, you do the actual scan. So what I can tell you would show up very nicely, use a profiler. And in the profiler, those sort of things just jump up at you. Sometimes you go, why is this method called 70 million times? And then you realize, by the way, one of the most expensive things that you will see, and this is quite annoying. Where is it? You will see something similar to this in your code. In many cases, one of the default reactions that we have for performance is add a cache. And then you see that some of your course now become cache management, looking up inside the dictionary. And that can be super expensive in some cases. Again, this is a huge performance improvement.
Exactly. Thank you. Another question, although we have like 3 minutes, and the question is for 3 hours of discussion from Jose is, what's your opinion about making garbage collection in .NET optional and using reference counting or resource acquisition
You would die. You would absolutely die. In order to do something like that, you have to have the entire system hanging on you. Try to imagine how would you handle this? When and how do I do ref counting or something in this case? This is a fundamental of the language, of the platform, and you cannot do that without everything else breaking apart.
Yep. But Jose, if you want to disable GC, I have created custom GC which does not garbage collect, so you can plug it in and then you will just have only allocations, which is not probably the thing that you were thinking about. And ID tools about allocations, I answered on
there are a bunch of, there is a Rosin analyzer that does that. There is a extension to Rider and ReSharper that does that. That can be incredibly helpful. Beware, it's addictive. And something else that is important, be very careful about what you're optimizing. It's very easy to get into crazy optimizations on stuff that runs once a day or at startup. I don't care if it takes me another 2 minutes to start. Well, 2 minutes I care. Another 2 seconds I don't care. It takes me to start up. I care about everything that happens during normal operations. And that thing is what I would optimize. One of the nice things that I get from using C# and .NET is that I have the ability to say, okay, here I'm willing to sacrifice and have really nasty code. And in this case, I can write far more expressive and easy to understand. And that matters a lot.
Exactly. Like I like those tools too, but don't be addicted and think about hot paths, measure. Like it doesn't typically, we don't care if whether it is 1 byte or 10 bytes or even 100 bytes if you are calling it once per day. So always measure. I answered with also the names of such tools for you. And very last question, very fast answer because we are slowly ending. So AO, async AO value task, reducing allocations there. Any thoughts?
IO sucks. Now, here's the issue. Which IO? Because there are multiple distinct things that you have to take into account. There is network IO, and we're now at the age where 10 GB is common, and 2025 is something that you just get. And if you don't do much, you can get to a million packets per second on Linux without going too crazy.
Mm.
For the disk, if you use NVMe, then you can also get to hundreds of thousands of IOs per second. The problem is, what sort of IO are we talking about? I'm a data. I care about durable writes. The moment that you have a durable writes, those numbers just goes away. Poof. And we're talking about 200, 500 actual durable writes per second, even on really good drives. And that has a lot of impact. On the other side, one of the things that we looked at is, okay, I can use IO ring in Linux, and there is now a IO ring in Windows as well to optimize concurrent IO. So the idea then is that what I'm going to do is whenever I need to go to the disk, I would rely, instead of memory map, I would rely on IO, an IO ring, and maybe rely either on the OS page cache or maybe manage my own cache or something like that. And it sounds good in theory, but then you realize that you have all of the management and overhead around that. When can I read? When can I write? When can I discard this buffer or stuff like that? And it ends up being the overhead of management around that being very high. The issue is, what sort of operations do you need? Notice that value tasks are about not doing asynchronous operations. It's for the very common things where sometimes you need to do an asynchronous operation, but in most cases, or in some hotspot cases, you can serve it directly from memory, and that can give you a better performance. But again, if you use value task, the code sucks basically, because you don't get to use simple await. You have to do, does it exist? Does it not exist? Have separate code paths and all sorts of stuff like that. So again, that's something that you do for your hotpots, for the things that it really benefits you, not for the standard behavior.
That's the super nice conclusion for the whole talk and all the answers. So thank you very much, Oren, for being with us. Thank you for being with us, and invite you all the time for future conferences. So you are always welcome, and have a nice rest of the day. See you
Thank
then
you very much.
in some place. Bye. Thank you.
Bye-bye.